All right, let's go back to momentum now. If you remember in the past that if you had an object that was moving along, and this object had a mass of 2 kilograms, and the velocity was 3 meters per second, that this thing has momentum. Momentum in this case was equal to 6 kilograms meters per second. All right. You also remember that momentum is conserved. So if you have I don't know, a car right here, and this car right here has a mass of 1,000 kilograms, and you have a big lump of clay. This is a 500 kilogram lump of clay. A crazy big lump of clay. And you smash it into the car. And you smash it in at 5 meters per second. And it makes an inelastic collision, which means that lump of clay basically sticks to the car. The car is just sitting right there, so the car has a velocity of 0. Car's just sitting right there. So that car is just sitting right there. This lump of clay comes flying in at 5 meters per second. It's going to hit the car, and the two will move off together. Once again, it's called an inelastic collision, and we've learned that in inelastic collisions, as with any collision, that momentum is conserved as long as there's no outside forces involved, as long as there's no friction, air resistance, that type of thing. There's no outside forces there involved. So what we have learned in the past is that the mass of the clay times the velocity of the clay plus the mass of the car, mass of the automobile times the velocity of the automobile is equal to the mass of the clay plus the mass of the automobile times final velocity. That momentum before is equal to momentum afterwards. So before the collision right here, the momentum of the car is 0. And so by using this, we can figure out the velocity of the car and the clay after the collision. So what we can say right here is we can say the mass of the car is 500 kilograms. The velocity of the mass of the clay is 500. The velocity of the car, the mass of the clay is 500. The velocity of the clay is 5 meters per second. The momentum of the car is 0. And afterwards, the combined masses now 1,500. And we can figure out the velocity of this thing pretty darn quickly. So this is going to be 2,500 divided by 1,500. So 2,500 divided by 1,500. You get a velocity right there. So it goes in, looks like about 1.7 meters per second. So the car and the clay will move off to the right. So this is something that you've done before. It makes sense to you. Momentum before is equal to the momentum afterwards. We've learned that energy was not conserved in this case, so that during this collision, that there's a lot of crunching taking place. The clay compresses. The car probably will make a dent in the back of the car. So there's a lot of crunching taking place, lots of friction, You hear sound, so energy is lost in this collision. But momentum is conserved. All right. As with everything else, with rotational motion, we've learned there's always a rotational component to this linear stuff. So in physics, what we say is we call this angular momentum. So when things rotate, they have angular momentum. So we use the symbol L. It is a vector. Is equal to, what's an L against the mass? It is the moment of inertia. And the part that's analogous to velocity is the angular velocity. So this right here is the equation for angular momentum. Angular momentum. And just with the same with linear momentum, angular momentum is conserved. So let's use the same principle. Let's see if we can figure out a problem right here. So let's say you got a merry-go-round. Whoa, I cannot accept that. Let's try it one more time. That's a little bit better. All right, you got this merry-go-round. Let's say it's spinning right here. At 2 radians per second. All right, and let's say there's a person right here on the outer edge sitting right here. The mass of the person, we'll say it's 60 kilograms. The mass of this metal merry-go-round, we'll call it 200 kilograms. And we'll say the radius of this merry-go-round is 2 meters. Pretty good size. 2 meter merry-go-round. All right, so this thing is spinning right here. The person's on it. The thing is spinning around. And then the person decides to go ahead and crawl towards the middle. And they're going to crawl to this point right here, which is 1 meter away. All right, so they're sitting on the outside, radius of 2. They're going to crawl towards the middle to 1 meter. All right, since we know that angular momentum is conserved, we can then say that the momentum beforehand, before the person crawls, is equal to the angular momentum afterwards. The angular momentum before is equal to the angular momentum afterwards. Angular momentum is conserved. So that says that I initial times omega initial is equal to I final times omega final. All right, let's go to work right here. This I initial right here, this merry-go-round initially has a moment of inertia of a disk plus there is a point mass, which is a person. And we'll call that, we'll call this R1 times omega, which is in this case 2 meters per second, or 2 radians per second is the initial omega. All right, afterwards, the person moves off to the middle, or climbs to the middle, which is going to be 1/2 mr squared. It's the same disk, so R is the same. And then we've got the person moving towards the middle. Mr squared. We'll call this position 2, which is where they are 1 meter away from the center. And this is what we're looking for. We're looking for the final angular velocity right there. All right, so that's basically the way it works. we have initial moment of inertia and initial angular velocity. As the person climbs to the middle, they get closer to the middle of the merry-go-round. This is going to make the moment of inertia smaller, and that's going to affect the final angular momentum. All right, so let's go to work here. I think I might need some more space. It's feeling that way. So let's go to work. So we have 1/2 the mass of the merry-go-round, which is 200. And the radius of the merry-go-round is 2. Plus we have the point mass, which is a person. So 60 kilograms times their radius. Initially, they're on the rim. So 2 meters squared times their initial angular velocity, which is 2. And let's see, I do that right. Get my parentheses correct. So we got this part, we got that part. That's all in parentheses times 2. Looks good to me. And yeah, I'm out of room again. Come on. So let's go ahead and give me a little more room here. And so now, on the other side of the equation, we got the merry-go-round itself has not changed the moment of inertia of this, just a merry-go-round. It's still a 2-meter merry-go-round. And we're going to add to it the person, which has a mass of 60 kilograms, times their new radius, which is now 1 meter from the center. And we're all going to take all that stuff right there, and we will have a final angular momentum. So there you go. All right, so go ahead and plug that thing in, see what you get. Get a angular velocity of about 4.9 radians per second. So you can see that we were spinning at about 2 radians per second. As the person goes in, that causes their angular momentum to, their angular velocity to increase. So you can look at it like this. We have an initial moment of inertia times the initial angular velocity. And then we have a final moment of inertia times the final angular velocity. And so if we take this thing and since momentum is conserved, angular momentum is conserved, if all of a sudden if I goes down and gets smaller, omega has to get bigger to compensate. If we increase our moment of inertia, omega will get smaller. So these two right here are inversely proportional to each other. Omega, if you want to spin slower, then make your moment of inertia bigger. You can see this with ice skating. You've all seen the ice skater, and I'm a little scared of what's going to happen here with my drawing. But here's an ice skater right here. Okay, ice skater. And I got ice skates on right there, right? And they got their arms out. You know what? I think I do that wrong. Usually they start out with a leg like this. They're like that. And they got their arms out like that. This ice skater's got pretty long arms. All right. Those arms are way too long. Okay. So we got arms right here. And this ice skater right here spins around, right? Spins around. It's got some omega right there. And so if you look at this situation right here, because the arms are out and the leg is out too, what we have is we have a big moment of inertia, which produces a small angular momentum. And what the ice skater does then is they go ahead and they, like I have a lot of experience with this here, is they pull their legs in. This leg that's out, they slowly pull it in. And then they pull their arms in as well. They usually put them above the head, like that. And what happens here is they pull that mass closer to the body, which makes the moment of inertia smaller, and that increases their angular velocity. So momentum is conserved right here, but by changing the position of the arms and also the leg right there, that causes their angular velocity to increase. So you can see that with lots of sports. If somebody wants to increase how fast they spin, all they got to do is tuck. You see it in gymnastics. You know, if you want to spin faster, what you got to do is tuck. As with the momentum problem we did earlier, this is only conserved as long as there's no outside. If we look over here, this problem we did, this only works if there's no outside forces involved. No outside forces means momentum is conserved. Now, with this new idea right here, is this angular momentum is conserved as long as there's no outside torques. So as long as there's no outside torques, torques could be caused by, in this case, friction. As long as there's no outside torques, then the angular momentum will always be conserved. Let's have you go ahead and try a problem. Let's simulate this ice skater. So this is the ice skater right here. This is the main part of the ice skater, the torso and the legs. This is everything right here. So the ice skater has a mass of 60, or at least the torso has a mass of 60 kilograms. And the radius of this torso is 20 centimeters. These are probably not realistic here, but just for fun. And you got the hands out there, and we'll just kind of ignore the arms right now. We got hands right here of 5 kilograms on each side, and they are 1 meter away from the center of the torso. So from the center of the torso, they are 1 meter away. So initially, this ice skater has a rotational or angular velocity of 80 meters per second. What they're going to do is they are going to, as they're spinning, they're going to pull their arms towards the center and hold their arms above the head, just like this. So can you figure out the final angular velocity? That is your question. I would like you to press pause now and figure it out. All right, press pause. All right, so in this situation right here, we know that the angular momentum is conserved. So we can say the initial angular momentum is equal to the final angular momentum. So what we have, let's see, this is going to be I initial times initial angular velocity is equal to I final times the final angular velocity right there. So what do we have? We have a, let's see, this is a cylinder, right? 1/2 mr squared, plus we have two hands out there. A hand is a point mass, mr squared, and we got two of them. We'll multiply by 2, and we have that initial angular momentum. And then afterwards, we have the, once again, we got the cylinder, which is going to be mr squared, or 1/2 mr squared. Now the hands right there are now right in the center. They are, I mean, the radius is 0 if we look at them as point masses. So believe it or not, but the hands won't make a difference in this case. So we'll just ignore the hands. And we have a angular velocity is what we're trying to figure out. All right, so let's see what we got. We got 1/2 the mass of the torso, 60 kilograms, times the radius of the torso, which is 0.2. Plus, we got the mass of the hands, which is 5 kilograms, times the radius, distance away from the center of the torso is 1 meter squared. We got 2 of them. And then on the right hand side, we have 1/2 the mass of the torso, 60 kilograms, times the distance away, which is, that cylinder is 0.2 meters. That's being squared right there. We're taking that whole thing right there, and we're multiplying by the final angular velocity. All right. So, if we go ahead and use a calculator, go ahead and show me what you got. Hey, by the way, it looks like I forgot to multiply by that omega right there. So don't forget to do that. So the initial omega is 80 radians per second. Okay, so don't forget to do that. We get a final angular velocity of about 750 radians per second, which seems almost unbelievable. I mean, we're going from 80 up to 750 just by pulling the hands in. That seems crazy. And these numbers may not be completely realistic, but if you look at this right here, the body part, because I have the mass of the body in such a small volume, you know, this radius is only 0.2. This part came out to be only 1.2, and the hands over here, because they're so far away from the center of mass, this part came out to 10. So on the left hand side, I did a moment of inertia of 11.2. On the right hand side, the hands are now in the center, so all we have is a moment of inertia of the body itself, which is 1.2. So you can see those hands make quite a difference. If you look at the ratio right there, 11.2 divided by 1.2, you can see that there's a factor right there of, let's see, 11.2 divided by 1.2. There's a factor right there of like 9.3 times. So the moment of inertia is 9.3 times greater before than afterwards. So we look at that inverse relationship right there, and we have an initial angular velocity of 80, and we multiply by that factor right there. That's where we get the 750 from. So this stuff is just some relationships with ratios. If you have decrease the moment of inertia by 2, your angular velocity will go up by 2, and vice versa. So lots of cool applications with this. This even is used to understand the formation of our solar system. So some great stuff to talk about. All right, have fun with it. Physics!